This is a presentation about predicting protein classification, a protein residue sequence-informed machine learning model. Following an introduction, I will tell you why I chose proteins, discuss my methodology, share my results, and how I analyzed them. My name is Jamie Dormar, and I'm graduating from the Lighthouse Labs Data Science Bootcamp. I have a background in biochemistry and life sciences. So why proteins? Because they're amazing. February's molecule of the month of the Protein Databank website is actually a really excellent example. It has intrinsically disordered dynamic domains that give it flexibility. It has structural domains that allow two units to click together, and it has catalytic domains that give it enzymatic functionality. Proteins are like highly informative data resources on nearly everything biologically relevant. For example, so diverse around the globe that it's a bit like geolocation for the specialists. Oops, too far. The fragment analysis of proteins is so specific, it's actually called mass fingerprinting. This enables us to learn amazing stories about survival and adaptations of organic life on Earth, even after death, including long-time death. Protein fragments remain viable in fossils. It's called paleoproteomics, and it's pretty amazing. Protein fragment analysis can also tell us the geolocation stories about the living. A rapid bioclassification system is essentially like having the biological geocaching and tracker codes for everything. A little shout out to my fellow enthusiasts who hunt tipware in the wild. The science is actually pretty close already. The at-home COVID-19 tests are actually a rapid identification of the nucleocapsid protein that I showed you earlier using lateral flow strip tests. So once protein fragmentation and analysis becomes portable, we're going to need an app for that. So here we go. My methodology, I started out by downloading the full archive from Protein Databank. Since the model I was creating as a supervised classifier, I needed to try to narrow down the number of classification labels. I also acquired the PFAM data archive, from which has just under 11,000 protein superfamily classifications. Kaggle also has an excellent data set with a bit of a side focus on protein crystallization specifications that are needed to generate the best crystals for X-ray crystallography. This is the tech stack that I used to create this model. All three sets had unique attributes which contributed to the model's final training and test data. And each set had a classification label that remained viable after cleaning and dimensionality reduction. I decided to move forward with the protein superfamilies. Other factors to consider: that for a rapid bioclassification system to exist, real-world data must be sensible. I needed to consider who would be collecting the samples and in what size or condition. And secondly, the monomeric sequences themselves are a language, so NLP seemed like a natural choice. When deciding the real-world processes I had to account for, I considered forensic investigators who'd have access to gas chromatography mass spectrometers. A full hydrolysis would result in individual amino acids, not too unlike a bag of words, so I simulated this with count vectorization. I also considered protease cleavage, for example, in research facilities, and simulated this with n-grams and using a character overlap and a vectorizer that would account for the sequential order of the peptides. The physical and chemical attributes of the individual residues were accounted for proportionately by multiplication with the protein count vectors and averaged for the net value of each protein. Each protein's acidity, hydropathy index, and net charge were all accounted for in this way. I also found another researcher's work using a similar data set and the same machine learning model in the hope that I could reproduce their results and from which to compare my own work to. This researcher was able to accomplish a 55.42% prediction accuracy score with 32 classification labels. My model was able to improve on his work with 82 classification labels and accomplishing a 66.45% prediction accuracy score. This is my confidence matrix. And I've got a little showing you the box here where there's room for improvement still on labels 53 to 65, for example, where you can see that one protein classification is commonly being mislabeled for the other, but off to a good start. That's all I have for you today. I hope you enjoyed the story as much as I enjoyed its content. Thank you.